So looking at circular motion, we have a centripetal force that keeps objects moving in a circle. The word centripetal, center seeking. So an inward force is needed to move an object in a circle or keep it moving in a circle. The force is directed inward. All right, we give it the symbol capital F, lowercase c, or subscript c for centripetal force. Velocity, all objects want to do is move in a straight line. All right, and they would keep doing that if it wasn't for that force. Well, velocity would therefore be tangent at any point along the circular path. So right here, all right, if we're moving counterclockwise, it's in a straight line off this way. Right here, it's in a straight line off that way. Right here would be a straight line, all right, kind of upper. It's not a perfect circle. I'm not a perfect circle drawer, but you get the idea. All right, we call it tangential or linear velocity. That is what V stands for here. Now, there's other equations to use to find that. We'll kind of look at those briefly. And then centripetal acceleration. All right, that's also going to be in the direction of the net force, in which case is the centripetal force, Fc. So two things always pointing inward: centripetal force, centripetal acceleration, right? So that word centripetal, center seeking, pointing towards the center. Velocity, tangent. Basically, if you were to make a point on any point along the circle, all right, it would be a straight line off. The equations for that, okay, centripetal force, mass times tangential velocity squared over r. And if centripetal acceleration is v squared over r, then you can take this guy, AC, and replace v squared over r with that. So it could look like that as well. There are other forms to that equation, but those are the ones that we would look at or see or deal with. I'm just going to briefly talk about rotation, revolution. Rotation is, all right, you're going around, imagine like a straight line going through your body, all right, from your head down to your feet, and then you spin around that axis. That's a rotation. All right, so the Earth itself rotates around its own axis, right, once every 24 hours. It's a day. And then a revolution is where you have an axis point outside of the body or outside of the object, and it rotates around that. That is a revolution. Okay, Earth goes about its own axis. Satellite, right, revolves around the Earth. Earth revolves around the sun. You do want to write down frequency. All right, so frequency, lowercase f, is defined as the number of revolutions per time. All right, number of cycles per second. I like that right there. So number of cycles. So if they said, all right, someone runs around a track 30 times in, 30 times in 1200 seconds. Okay, what is the frequency? You would need frequency in certain problems in order to help solve for the linear velocity or tangential velocity, v. This will be used at some point. All right, so just frequency, lowercase f, number of revolutions per time, write down number of cycles per second. So cycles can mean anything. It can mean like when we get into waves, it could be like oscillations, their back motions, like an up and down motion, a sine wave, how it goes, right, traces up, down as it moves across, and just that the unit is hertz. All right, any other information you need, you'll have to go back and see. You can go back and look at this. All right, so frequency, f, number of cycles or revolutions per second. All right, and the unit we want is the hertz, capital H, lowercase z. And then period. So write down period is capital T. Time for one revolution. And then this bottom bullet. All right, most of the time the unit for that is going to be in the seconds. And frequency and period are the inverse of one another. So if I said, wow, something has a period of 2 seconds, it means it takes 2 seconds to make this circle, all right, to make this full lap. What would the frequency of that be? Frequency would be 1 over the period. If the period is 2, frequency would be 1 over 2 or 0.5. And that unit would then be hertz. Okay. So period, capital T, period, and frequency are inverse of one another. So if you have one of them, you can find the other by just dividing one divided by the other guy. All right, so frequency is 1 divided by the period. Or if you know what frequency is and you need to find T, period, you do 1 divided by the frequency. Okay. We're not going to really worry about angular speed. This is just kind of showing, right, guys, at any single circular point, all right, this thing is moving counterclockwise, the arrows, and how they would be. You can just write tangential speed, V, is 2 pi r over the period, or 2 pi r times the frequency. So tangential speed, tangential or linear speed, V. And V is equal to one of these two equations. All right. So we'll have that. Just wanted to give you show you what that is. Okay, if you need to go back and write this in, you can leave yourself a little bit of space, just because I want to kind of skip through this as quick as possible. All right. This is a very good, or this is much needed for the conceptual part of this. So uniform circular motion. All right, your tangential speed is constant at every point that has the same radius. But the farther you are from the center, the greater than tangential speed is. Now your rotational speed, basically your frequency, is the same. So my awful example is thinking about horses on a carousel, right? Or merry-go-round, whatever the hell they're called. How they would design it is, all right, from that center point, they have a rail that goes straight out. And these 4 dots are to represent horses. So as you go up, or as you get farther from the outside, right, they're all on that same rail. So do you guys tell me, is this piece of metal, this piece of steel, all right, where the horses are kind of attached to, is the inside part of that going to make more laps around than the outside part? No, that can't. The metal is not going to bend like that. So that's why the rotational speed is the same. Frequency is the same. All the horses are going to make the same amount of laps around. But the tangential speed is not. And if you look, right, the farther you are from the outside, all right, for this bar to keep in line the entire way, just to go from here to here, this slice of the pizza, the outside horse, look how much more distance it has to cover, all right, especially in comparison to the inner horse. So it has a greater tangential speed, but the same rotational speed, because they're going to make the same amount of laps. But yes, essentially, they would have to move faster. They would have to have a faster speed, because if you look at how far away it is, how much more distance it would have to cover. So if I basically had a long 10-foot wide, pole in the ground, and pole in the ground with a 10-foot wide beam, and I had 4 of you guys try and push it at the same speed. You have to all stay together. Well, the person on the outside is going to have to basically be running, while the person on the inside maybe a faster walk, all right, by turning this thing around. If you were all to stay in the same, all right, on that same line, on that same rail. So I do want to make sure you guys understand that. So let's say hypothetically, or maybe not hypothetically, years, hopefully down the road, you guys have kids and you want to take them on a merry-go-round or carousel. Let's say your kid is a little daredevil. He wants to go fast. Which horse would you want to put him in, the inside or the outside? The outside, right? He wants to go faster. Okay, or you have one of your kids is maybe a little bit scared of rides at first, but they kind of want to go on. Where would you want to bring them? On the inside, right? They're still going to make the same amount of laps around, but it's not going to be going as fast. Okay.
Wait.
What?
How does a carousel go at different speeds?
All right. So again, if we're looking at this,
So does it all spin together?
Yes. But as this thing turns.
Well, I understand it's much distance, so it's got to.
So that's what it is. So yes, they're all gonna turn at the same frequency. It's gonna they're all gonna rotate around the same amount of time. So each horse on that beam is gonna make the same amount of laps around. But because this one has to move at a farther distance that it has to cover than the inside one, this one is going to have to basically be moving at a faster speed. So if you guys we had a hole in the ground and like a 10-foot beam, and I had 4 of you guys hold on to that and try and move around at the same rate, that person on the outside is going to have to be moving a lot faster in comparison. Does that make sense? Okay. Okay, so we're not going to write all this down, but how you go about solving this. All right, person travels once around a circular track with a radius of 20 meters in 3 seconds. Calculate the period. How do I know what the period is? The period is the time it takes to make one lap, one complete circle, one cycle. So they told you right here that they do once around a track in 3 seconds. So that's your period. So period is 3. And then frequency is 1 divided by the period. So 1 divided by 3, which is 0.33 repeating, and that would be hertz. And then the tangential velocity, v, you can do one of 2 ways. 2 pi, you just type into the calculator. R is the radius, which was given. And then you can either times it by 0.33, or you can divide by 3. And you're going to get right around 41.9 meters per second. All right, RPMs, you would just have to change this into hertz. So frequency in hertz, you'd have to divide that by 60. Once you get the frequency in hertz, you do 1 over that to get the period, and then plug it into one of your linear or tangential velocity equations in order to get the piece here. Okay, we're not going to go through all of this right now. So like your merry-go-round carousel, how does the tangential velocity vary with the radius? So as this, the tangential or linear speed is going to increase as the radius increases. So it's basically the same thing as I said. The farther away you go, the more that is going to wind up being. So it increases the further you're from the center. All right. How does the frequency change with the radius? It doesn't. You're still going to make the same amount of laps around. The inside horse, second inner, middle inner, and then outer, they're going to wind up going around the same amount of times. Okay. So we already have this kind of up on the board. All right, centripetal acceleration, A sub c is v squared over r. Always points towards the center. All right, so we have kind of what this was looking like. All right, this is straight off of a website, Physics Classroom. An object that is moving clockwise. You guys know what clockwise goes to? Looks like? All right, because you would basically, the thing would be turning from A towards B towards C. All right, which vector below represents the direction of the velocity when the object is located at point B? What arrow would we say then? It would have to be D, all right? It would have to be D, perpendicular, all right? So really there can only be 2 potential options if it was at point B, straight up or straight down. And since this thing is moving clockwise, it would be moving from A to B to C, so it would be like a straight line kind of off this direction like C, right to the right at point A, straight down for point B. What represents the direction of the acceleration vector if the object is at point C? Well, what is the word that comes in front of our acceleration? Centripetal, which means center seeking. So basically, if you're at point C, which letter, A, B, C, or D, is going to point towards the middle? B. All right. What about the velocity vector if the object is at point C? it would have to be A. And then they want to know what about the acceleration vector if the object was at point A? D. It would have to be going straight down towards the center. Okay, there's a couple problems here. We're not going to write down right now. This would have been like kind of maybe a potential do not question for tomorrow, but we're going to kind of we're running through this at a little bit of a quicker pace. Essentially, what you need to make sure you know are your variables. Meters is going to be what we want our radius to be in. Meters per second squared would be what our acceleration is in. Meters per second, our velocity. Unless something happened where you were given, like in one of those two example problems, all right, how many laps around you go in a certain period of time, and figure out what v or frequency or period is in order to help find v. And then these would be the kind of solutions to that. If you needed to go see these or want to try them out yourself, you can go back and pause and see how you wind up doing. Centripetal force. Again, center-seeking force always points towards the center. All right, so this is the force that is needed to keep an object moving in a circle. And that's going to increase if the mass of the object increases. So I don't know if you guys ever did this when you were younger, if like your dads ever just kind of grabbed you guys by the hand and just like picked you up and just started like spinning you until you like started moving around, or you have like a younger cousin or sibling that you may have used to do that to. All right, so basically think about this. If you're doing that with a heavier kid, right? If I were to do that with like a 3-year-old versus one of you guys, all right, mass is increased. So I would need to apply a much larger force in order to move you guys in the same speed, all right? Move you in a circle at the same speed. So the force would increase if the mass of the object increases. And the radius of the circle in which it's traveling decreases. So like the tighter it is, so if I had to move you out and like both your arms were extended, all right, it's a little bit easier, but if I bring you in closer, I'm going to have to wind up pulling with a much larger force. So think about it this. You're driving in a car, you're going on or off the highway. Are the ramps usually just straight, or they're usually some kind of curve? Usually some kind of curve, right? Or if you're just driving on a road, now most of you guys are new drivers. If you're going around a road that has a very tight curve, right, or a very like kind of sharp turn, usually there's signs that say what? Slow down, reduce speed, like only go around it at 25 miles an hour. If you're trying to do those turns at faster speeds, you would need a much larger force of friction between the tires and the road in order to keep that thing in contact. So if you're trying to whip one of those turns, one of those very tight turns at a fast speed, there's not enough friction force in order to kind of keep everything in turn. So chances are the car will wind up sliding out or flipping. Tires pop potentially as well, so not the best. And then they just kind of show in here the inertia. All right, so remember, inertia objects they're resisting change in motion. Once an object gets moving, it wants to move in a straight line. So if you're spinning a ball, all right, attached to a string, all right, your hand's holding the string, you're spinning it over your head. At any single point, the velocity is moving at a straight line. It's moving at a straight line. So right here, it would be moving straight down. If it were down here, it would be moving straight to the right. Right here, it's moving straight up. And at point B, it's moving straight to the left. Now, if the string breaks right there, all right, this is just a quiz and test question. The object, all right, the ball is not going to move in a curved pattern. It is just going to move off at a straight line tangent to its speed. Now, if we're doing that on a flat surface, you'll be able to see that a little bit easier. But if it's in the air, obviously there's some other forces that will take play afterwards, like gravity causing it to turn and move to the ground. So this is just like the one before. The only addition is force, in which case all the answers with force would have to be going towards the center, just like the acceleration. But the velocity is still tangent. So force vector at point A should be towards the center, so straight down. Force vector at point C, well, if the center is here, it's got to be like at a northeast angle or B. What about velocity at point B? If this thing is moving clockwise, so that would be straight down. Velocity at point C would be kind of up this angle here, northwestern-ish. Direction of acceleration at point B would be straight to the left because that would be inwards towards the center. Okay, so how we're going to do this one. So just kind of, if you guys can, we're going to sketch these out really quickly because these are going to take play into our other thing. Let me see. Can I wind up? No, I can't. Okay. So what happens to the centripetal force for an object in circular motion? All right. Or the centripetal force is 10 newtons. What would happen if the mass were to double? So if the mass were to double, all right, so this is how we're going to do this. So the first one, M doubles. Second one, R doubles. Third one, V doubles. And fourth one, M to the 1/2. And the last one, centripetal force if the radius is halved. Okay. So we're going to just add these. Oh, this was from our test, so we don't need that. All right, so centripetal force mv squared over r. You guys are familiar with the ones equation. We have basically what I call this anytime we make a proportionality type of a problem. So for the right now, m would be a 1 times velocity, or your tangential or linear velocity, squared, which would be a 1, and r is would be a 1. So these guys, definitely write these down. This will help with, all right, your assignment.
There we go.
Better?
Yep. Easy.
All right. So when they say the mass doubles, nothing else is going to change except for the one that was our m. So since m would be here, I'm going to make that a 2. Nothing else changed, so our v stays a 1. That has to be squared. R stays a 1. And then you just kind of work this math out. 2 times 1 was, or 1 squared is 1, and 2 times 1 is 2. 2 divided by 1 is 2 times the original centripetal force. Now, in that problem, they said if the centripetal force was originally 10 newtons and the mass doubles, what would the new force be? You just substitute in, all right, 10 for FC. So 2 times 10, new force would be 20 newtons. What about if R doubles? What would happen, guys, if R doubles? So centripetal force is basically mass times v squared over r. So this is my m, my v squared, this is r. When they said that mass doubles, we changed the 1 that was an m to a 2. Nothing else happened, so we're going to keep the v and r 1. So when you, because it's a proportionality, so like if the mass doubles, what's going to happen, you're going to wind up having or needing 2 times the centripetal force. So like in that problem from the notes, this is not what I wanted. So they're saying, okay, if the original centripetal force of this thing is 10 newtons, like how is it going to wind up being? So like if you just worked out that problem, it would be, you could write it as like, instead of 2FC, you could have said like 2 times whatever the centripetal force was. They're telling us in that problem that the centripetal force is 10. So I just wrote 2 times Fc, all right, for centripetal force, and I just plopped in the 10 that they originally gave us. But it's still the same thing. So if we double the mass, what happened to the original centripetal force? It would now be 20, and it doubled. What about if the radius doubled? All right, they didn't tell you anything about the mass, so we're going to keep that at 1. The v didn't change, so we keep that at 1. That just still has to be squared, even though it's a 1. But r doubles, so the r that was a 1 becomes a 2. 1 squared is 1 times 1 is 1. And then 1 divided by 2 is just going to be 1 over 2, or 1/2 the original centripetal force. And if the original centripetal force is 10, what's half of 10? 5 newtons.
And that's for R double?
Yeah, that's if the radius doubled. So if the radius is doubled, the centripetal force gets cut in half. All right, what about if the velocity doubles, our tangential velocity doubles? Well, mass doesn't change, so that stays a 1. The v squared, right, which became our 1 squared, that would become a 2 because it says it doubles. But you still have to add that squared to it. And in there, they said nothing happened to the radius, so we're leaving that. 2 squared is 4. 4 times 1 is still 4. And 4 divided by 1 is still going to be 4. So you would wind up needing or having 4 times the centripetal force. So 4 times 10, 40 newtons. So just based off of those 3 variables in the equation, which one affects the centripetal force the most? V. Why? Because it's squared. So it's going to have the most drastic effect on it. All right, what would happen if the mass was to be cut in half? Well, m would become a 1/2 times v squared over r. 1 squared is 1 times 1/2 is 1/2. 1/2 divided by 1, still 1/2. So 1/2 the centripetal force, in which case that would wind up being half of 10, or 5 newtons. And then the last one, the radius is cut in half. Mass and velocity are 1s, but now this dude is a 1/2. 1 squared is 1, divided by 1. I'm sorry, 1/2. Jesus. 1 squared is 1 times 1 is 1. And 1 divided by 1/2, when you type it into a calculator, or you don't need to, that becomes 2. 2 times the centripetal force. And so if the original force was 10, 2 times 10, 20 newtons. And then if you had other ones that had combinations, you just kind of play around with them and just simplify at the end. So what happens to the mass is directly going to affect the force. I doubled the mass, the force doubled. I cut the mass in half, the force got cut in half. R, that is, it's the inverse. So when I doubled R, the force got cut in half. When I cut the radius in half, the opposite happened. The force would double. So those are kind of what our proportionality problems look like. So that should be simplistical. And now let me see. No, don't care about this. Don't want to do this. The unit for these guys, forces in newtons, mass will be in kilograms. and your tangential velocity in meters per second. All right, so the first of our two assignments. One should be relatively easy, and you just because it's very similar to what we did, and then there's just some vocab from the worksheet that we just did, or from the notes. So what I'm handing out to you right now. What I'm handing out to you guys right now, we're going to go over. This one actually has some like other problems besides the conceptual problems like those. All right, here we go. All right, so guys, this should be relatively simple. What does the term centripetal mean? You're not wrong. Center seeking. What is the direction of the acceleration and centripetal force? They always act towards the. Yeah, not a trick question. Going in towards the center. So they want you to look at these. In circular motion, identify the following as either changes or stays the same. The speed of the object. So, yeah, uniform circular object, right? Circular motion. The speed of the object is always going to stay the same. So those horses on the merry-go-round, all right, well, once they get their speed, they're going to stay the same. What about the direction of the centripetal force? So I like the way you answer that. So I'm going to say yes, but it's the answer to how I want it worded is going to be right. So as this thing is moving around, looks like clockwise. Yes, it's always pointing towards the center, but because this object is constantly moving, right, it would constantly be pointing towards, all right, the center. Can't really do this exactly how I wanted to, but yeah, it would basically be here, pointing towards the center. When the object is here, it's pointing towards the center. If it's here, it's pointing towards the center. So because of that, we're going to say that it is changing. All right, because the direction of the object is changing, the direction of the centripetal force is changing, but it is always towards the center. What about the magnitude of the centripetal force? Well, as long as our speed is constant, the mass of the object doesn't change, and we're going around the same radius, yeah, that number is not going to change. So it's going to stay the same. What about the velocity? Good. It's going to change, and why? Because if we broke it down into the simplistical terms, velocity is essentially just speed with a direction. And since the direction is constantly changing, the velocity, therefore, is constantly changing. Anytime you have a change in velocity, the object is accelerating, and the object accelerates in the same direction as your net force. In this case, the net force would be your centripetal force. So this does change. All right, the direction. The mass of the object, though, it's chilling. It's staying the same. Okay, so if you had to draw in the acceleration vector, I want you to draw in acceleration, centripetal force, and velocity at this dot. So velocity is always, guys, basically a straight line at whatever point we're talking about. Now, if this thing is moving clockwise, it would be like that. This one would be over here. Okay, you'd have something like this, something like this. like a spinning ninja star. All right, so this guy here, straight down, you guys will do that and label that letter V. And then arrow in. And then a second arrow in, you can maybe just make it slightly above it. All right. FC should be the larger vector. And AC should be the smaller of the two arrows. Why would that be? Well, because centripetal acceleration is v squared over r, and centripetal force is mv squared over r. So I'm literally multiplying this whole value by m. So yeah, it should be a little bit bigger. All right, and then the back sides. There's a lot of numbers and a lot of things that I wrote on here. Frequency is lowercase f, number of cycles per second. Period is capital T, the time it takes to make one cycle, and what their units are. Our other units here, and yeah, it should have anything and everything that you do need. So let's roll through it and kind of figure out what's what. A ball with a mass of 2 kilograms. So yeah, you're gonna definitely want to label everything here because you need to know what you got in order to where you're gonna need to go. So we got 2 kgs on a string swung in a horizontal circle with a radius of 0.5 meters. So radius, we want it in meters. Mass, we want it in kilograms. And a tangential velocity, that is letter V, 4 meters per second. And what do they want? Centripetal force. So FC is my question mark. We have the equation. mv squared over r. Only squaring v. All right, you only square v. So the math for that would be 2 times 4 squared over 0.5. All right, so 4 squared, 16, double it, 32, divided by 0.5, which will double it again. .64 newtons. Okay, next you have race car, mass 500. Radius 25. What's funnier than 24? 25. SpongeBob? No. All right. Anyway, moving on. And then if the car experiences a net centripetal force of 50 newtons, FC will be 50 newtons. What is the velocity? V is my question mark. So this equation here has our V that we need. So V will equal, all right, our centripetal force times the radius divided by the mass and square root. So I'm going to write that equation as FC times R over M, and then I'm going to square root that. So, all right, the most common mistake with this, guys, is everybody does the math inside correctly, then forget to square root. So it should be 50 times 25 divided by 500, and then square root. So 50 times 25, which is 1250. Divide that by 500. It's 2.5. And then the square root of that should come out to be approximately 1.58 and change. Meters per second squared. A hockey puck, mass 3.5 kilograms. I feel like it's a little bit heavy for a hockey puck.
3 kilos?
Yeah, no, that's gotta be way too much. This must be like,
That's way too much.
yeah, it's like a hockey puck for
Yeah,
giants.
blind people size and stuff.
What?
Yeah, they make them. They're like huge, dude, and they have bells in them.
Okay. Huh?
3 kilos is
The-
almost
the-
like
I don't know.
half.
More, I didn't know that. More. Huh? Anyway, moving on. That was
Yeah, that's
low key, kind of funny, but moving on here. Puck has a tangential velocity of 5 meters per second. Net centripetal force, yes, of 28. Who said that one? It's good. It's good. And they're looking for R. What's a
Velocity still meters per second squared.
no, velocity meters per second. Acceleration, if they ask for it, that will be meters per second squared. Okay. Solving this for R. You're basically just going to swap these two. Yeah, you just basically swap these two. So R would equal mv squared over fc, which we also have written here. It's just a little bit more funkadelic, but
Sounds like Mr. Mackey from South Park.
okay. Anyway, moving on. Mv squared over centripetal force. All right, you guys will be able to finish that one out because you already have all your values here. And let's just take a look at the little last one here. A truck is traveling around a circular turn with a tangential velocity of 40 meters per second. If the radius of the turn is 20 meters and the truck experiences a centripetal force of 18,000 newtons, what is the mass of the truck? Damn. All right. So let's see. We got V, 40 meters per second. We got R, 20 centripetal force, 18,000 newtons, and a mass is my question mark. So in order to do this one, we have an equation at the top. This can be rearranged for mass as centripetal force times radius divided by v squared. So m will equal centripetal force times radius over v squared. All right. Now just be careful with this when you throw it into your calculator. Multiplying f, c, and r on top, great, but then you divide it. I would just divide and then put your v squared in parentheses and then hit your equal sign, and you should be good. All right. So finish those guys off real quick, and then we will get on to our next piece. Yes, sir.
When you like square a number, like on top, like mv squared, do you not square the number? Like do you not square v before you multiply?
I do, yeah. So I would always, like, if I were writing that out again, it'd be 3.5. I like to do it like v squared and then divide by whatever else I need. So in my calculator, I'm always doing that first if I need to or if I can. Right, so my 5 squared first, then times my whatever else, and then divided by the last thing. And
Number 5 on the top. Well,
yeah, so I did 4 squared, 16, that times 2, 32, and then when you divide it by 0.5, it's like doubling it. So it winds up becoming 64. All right. So I'm just going to briefly show this, and then I'll hand it out to you guys. This will be your homework, which you'll have time to start in here. All right, proportionality problems, just like the ones that we did. This thing wants you to rank these, which you guys should be able to do right this second. Where's the mouse? Excuse you. There you are. So you have A, you have B. It's ugly. I don't like that. Okay, the idea is they want to know rotational speed. So let me get a different color for this one. They're all in the same bar. And then as this thing goes, which object has to cover more distance as this thing rotates around? Who has to cover the most distance, A, B, C, or D? D would have to cover the most.
Oh, D would.
Yeah, D would have to cover the most distance here. Then C, then B, then A. So when they want you to rank them, all right, from greatest to least tangential velocity, it should be D, C, B, A. But about the same rotational speed is just, hey, they're going to make the same amount of laps around. So they all make the same amount of rotations, therefore have the same rotational speed. So you just write same for all of them. And then a couple little things on the back. All right. Which you can always go back into the notes to figure out. Okay. Boom.